Have you ever wondered how your phone can take a call that's just full of static and somehow clean it up? Or how it can sharpen a photo that came out all blurry? Well, today we're going to pull back the curtain on the secret superpower that makes all of that possible. It's a core concept called a linear system.
I mean, really think about it. Your phone takes this messy, complicated problem, like a noisy call or a blurry image, and it just fixes it. It feels like magic, right? But it's not. It's actually a really powerful strategy. You break one big, complicated problem into a whole bunch of simple little ones.
In that strategy is our first big idea today. It's a classic divide and conquer approach. But instead of armies on a battlefield, we're applying it to the signals that are all around us. You know, audio, images, radio waves, you name it. So, let's see how this actually works.
Okay, so this slide basically shows the entire trick in one picture. The strategy is called superposition. We take a complex signal and we break it down, we decompose it into much simpler little pieces. Then we process each of those simple pieces one by one, which is way easier, and finally we just add them all back together. We synthesize them, and boom, the complicated problem is solved. It's kind of like trying to multiply, say, 2041 by 4 in your head. You don't do it all at once, right? You break it down. You do 2000 times 4, then 40 times 4, then 1 times 4, and you just add up the results. That's superposition.
But, and this is a big but, here's the catch. This superpower, this incredible divide and conquer trick, it doesn't work on everything. It only works if one very specific condition is met.
That's right. This superpower is exclusive. It only works on a special category of systems, the actual processes that are doing the filtering or the amplifying or the cleaning up of a signal. So, what are these special systems called?
They're called linear systems. You can think of a system as just any black box that takes an input signal and spits out an output. But a linear system is a special kind of black box. It's one that follows a very specific set of mathematical rules. And it's because it follows these rules that our divide and conquer strategy is guaranteed to work perfectly, every single time. And luckily for us, most of the systems we really rely on in science and engineering just happen to be linear.
This really brings us to the heart of the whole thing. What are these rules? What's the secret handshake that lets a system into this exclusive linear club?
All right, so we're going to put these systems to the test. First, we'll look at a couple of quick, intuitive checks that'll give you a kind of gut feeling for whether something's linear. And then we'll get into the formal mathematical proof.
Okay, so here are the two big intuitive clues you can look for. First is something called static linearity. If you graph the system's input versus its output, you should get a perfectly straight line that goes right through the middle, through the origin. The second clue is sinusoidal fidelity. This just means if you feed a pure sine wave into a linear system, you are absolutely guaranteed to get a pure sine wave out. Now, it might be bigger, it might be smaller, it might be shifted a little, but it's still going to be a perfect sine wave of the exact same frequency.
And this illustrates that first test perfectly. On the left, you've got a simple resistor. We all know Ohm's law. Current is directly proportional to voltage. You double the voltage, you double the current. It's a perfect straight line. That's linear. But on the right, you've got a silicon diode. Look at that relationship between voltage and current. It's this big dramatic curve. That is absolutely not a straight line. That's nonlinear. Simple as that.
So we've got the gut check down, but for the engineers and scientists out there building our world, a gut feeling just isn't going to cut it. They need formal proof, and that proof rests on two core mathematical pillars.
The first pillar is called homogeneity. It's a really fancy word for a super simple idea. Whatever you do to the input size, the same thing happens to the output size. So, if you double the strength of the input signal, the output signal strength also doubles. You triple the input, you triple the output. It scales up and down perfectly.
And the second pillar is additivity. And honestly, this quote from the source material just explains it perfectly. Imagine you're on a phone call with your Aunt Edna and your Uncle Bernie, and they're both talking at the same time. Their two separate voice signals are being added together by the phone.
Now, here's the crucial part. Because the telephone network is a linear system, you hear Edna's voice plus Bernie's voice. The signals just pass right through each other without messing with one another. You don't hear some weird, monstrous new creature called Edna Bernie. That's additivity. And any system that has both homogeneity and additivity, well, it passes the test. It is officially a linear system.
So now that we know the rules of the club, we can get back to our superpower, breaking signals apart.
See, because linear systems follow these rules so perfectly, we can decompose complex signals in some really, really clever ways.
We're just going to touch on two of the most important methods out there. The first one is called impulse decomposition, which basically breaks a signal down by time. The second is the famous Fourier decomposition, which breaks it down by frequency.
Impulse decomposition is actually beautiful in its simplicity. It just breaks a signal down into a series of tiny little spikes, or impulses, where each one represents a single individual moment in time. This lets us see how a system responds to a really short, sharp input, which turns out to be a key building block for all sorts of advanced analysis.
But Fourier decomposition, man, this one is even more amazing. It reveals that any complex signal, I don't care how jagged or noisy it is, can be perfectly recreated just by adding together a unique combination of simple sine waves. It's like finding the exact recipe of pure musical notes that make up a complex sound. This one insight is, and I'm not exaggerating, the foundation of modern signal analysis.
Okay, so let's tie this all together now. We've talked about some pretty abstract ideas, I know, but their impact on our actual daily lives is absolutely immense. This isn't just some textbook theory. This is the engine that runs our digital world.
Now here's a super common point of confusion that's really worth clearing up. Multiplying a signal by a constant number, like turning up the volume knob on your stereo, that is a linear operation. But multiplying one signal by another signal is fundamentally nonlinear. So why is that? Well, when you multiply two sine waves of different frequencies, you actually create brand new frequencies that weren't there in the original signals. And that totally violates our sinusoidal fidelity rule, right? What comes out is no longer a perfect sine wave of the input frequency.
So where do we actually see all these systems in the wild? Well, linear systems are literally everywhere. The amplifiers and filters in your stereo, the way sound travels through the air, even the process that makes a photo blurry in the first place. But nonlinear systems are all around us too. Think of a guitar distortion pedal that creates that awesome crunchy sound, or a digital logic gate that's either on or off, or an amp that you push so hard it starts clipping the signal.
So let's just recap the whole story here. The big picture is this. To fix really complex problems like noise and blur, we use this amazing divide-and-conquer superpower called superposition. But that superpower only works on a special class of systems called linear systems. And we know a system is linear if it just follows two simple rules: homogeneity and additivity. That simple, elegant foundation is what makes so much of our incredible digital tech even possible.
It's pretty amazing to think that those two simple rules, scaling and adding, are the bedrock for everything from clearing up your phone call to exploring the universe with giant radio telescopes. It really makes you wonder, with a principle this powerful and this fundamental, what completely new technologies will it build for us next?